You are sitting in a room, surrounded by objects that possess a reassuring weight and a definite location. You assume that the walls around you, the floor beneath your feet, and the very air you breathe exist independently of your presence. You believe that if you were to leave this room, the geometry of the space and the matter within it would persist in exactly the same state. This is the foundation of your reality, the conviction that the universe is composed of local, objective things that interact through cause and effect. However, when we look at the results of our most precise experiments, this foundation does not simply crack, it vanishes. The data suggest that the qualities we assign to the physical world, solidity, position, and even the flow of time, are not inherent properties of the universe itself, but are instead artifacts of how information is processed. We are faced with a measurement that is internally consistent, but globally incompatible with our intuition.
Central conflict we must explore is no longer whether our perception is flawed, but whether the objective reality we think we are perceiving exists at all. The persistence of local realism. You believe that an object has properties even when it is not being interacted with. This concept, known as realism, suggests that a moon exists in a specific orbit regardless of whether an eye or a telescope is pointed toward it. It is the silent assumption that provides the architecture for your daily life. When you place a key in a drawer and close it, you do not entertain the possibility that the key ceases to have a shape, a mass, or a location simply because it has left your field of vision. You rely on the world being composed of things that possess inherent characteristics, existing independently of any observer. This is local realism. The idea that objects are influenced only by their immediate surroundings and that their state is a fixed, objective fact of the universe. This perspective is not merely a psychological comfort. It is the logical basis for all classical physics. For centuries, the work of Isaac Newton and those who followed him was predicated on the stability of the object. If you measure the velocity of a moving body, you are reporting on a value that the body already possessed before you arrived with your instruments. The measurement is an extraction of truth, not a creation of it. We view the universe as a vast mechanism of clockwork, where every gear and spring has a definite position and a definite momentum, moving according to local laws of cause and effect. In this world, distance is a real barrier, and no influence can travel faster than a signal sent through space. However, as our ability to probe the smallest scales of matter evolved, this intuitive framework began to show signs of structural failure. We discovered that when we move from the scale of moons and keys to the scale of atoms and subatomic particles, the concept of a pre-existing property becomes impossible to verify. The data started to suggest that a particle does not have a position until it is detected. Before the interaction, it exists in a state of superposition, a mathematical description of potentiality, rather than a physical description of a thing. This is not a statement about the limitations of our technology. It is a statement about the nature of the particles themselves. The conflict arises when we try to reconcile this with our macro-scale experience. If the atoms that compose the moon do not have definite properties until they are measured, how can the moon itself exist in a fixed orbit when no one is looking? We have long assumed that the large-scale world is simply the sum of its smaller parts. But if the parts are non-local and indeterminate, the stability of the whole becomes an observational paradox. We are forced to consider the possibility that the solidity of the world
is a collective illusion, a persistent statistical average generated by trillions of microscopic events that, individually, possess no reality at all. This leads to a chilling realization regarding the nature of space and time. In a local realist universe, things are separated by gaps, and those gaps dictate how information can flow. But if realism is false, the gaps themselves may be irrelevant. We find ourselves in a reality where the moon's existence may be contingent upon a complex web of interactions that we are only beginning to quantify. The persistence of the world around you is no longer a guaranteed fact of nature, but a phenomenon that requires an explanation, one that the current data suggests is far more alien than we are prepared to accept. We are left looking at a moon that may only be there because the universe has already accounted for our gaze. The Einstein-Podolsky-Rosen paradox. In 1935, a challenge was issued to the completeness of our understanding, suggesting that if the world were truly as the new physics described, it would require a connection between particles that defies the speed of light. This critique, authored by Albert Einstein, Boris Podolsky, and Nathan Rosen, was not intended to support the strange new claims of quantum mechanics, but rather to expose what they believed was a fundamental flaw in its logic. They argued that the universe must be local, meaning that an event in one part of space cannot instantaneously affect an event in another. To Einstein, the idea that two particles could remain intrinsically linked across vast distances was spooky action at a distance, a concept that felt more like mysticism than rigorous science. The argument centered on the concept of entanglement. According to the mathematics of the time, it was possible to create a pair of particles that shared a single, unified existence. If you measured a property of one particle, such as its spin or its position, you would instantly know the state of its partner, regardless of whether that partner was an inch away or on the other side of the galaxy. Einstein and his colleagues argued that since nothing can travel faster than light, the second particle must have already possessed its properties before the measurement took place. They suggested that the theory was simply incomplete, that there must be hidden variables or underlying instructions that we were failing to see. This paradox forced a confrontation between two irreconcilable views of reality. On one side was the belief in a definite, local world where information is constrained by the geometry of space. On the other was a mathematical framework that suggested the universe is fundamentally non-local, where the separation between objects is a secondary detail rather than a primary truth. If the EPR argument was correct, then quantum mechanics was merely a temporary tool, a placeholder for a deeper, more traditional theory. But if the paradox remained unresolved, it implied that our most basic assumptions about the independence of objects were wrong. The implications of this conflict are quietly disturbing. If two particles can be entangled, then the entire universe, which began in a state of extreme density, could be seen as a single, interconnected system. In such a system, the concept of individual objects becomes a convenient fiction. We treat the things around us as separate entities because our senses are tuned to a specific scale. But the EPR paradox suggests that at a fundamental level, the boundaries we perceive between matter and space do not exist. There is no such thing as an isolated system. For decades, this remained a thought experiment, a philosophical disagreement between titans of physics. There was no way to peer inside the particles to see if those hidden variables actually existed. The world continued to appear local and stable, while the mathematics continued to predict the impossible.
It was a stalemate that allowed us to ignore the underlying tension in our West.
Description of reality. We operated under the assumption that the paradox was a symptom of our ignorance, rather than a description of the world itself. However, by framing the problem so precisely, Einstein unknowingly set the stage for its eventual testing. He demanded that the universe choose between locality and completeness. He was certain that the universe would choose locality, that it would prove to be a place where things only happen here or there, never both. He could not have known that, when the measurement was finally made, the result would not just challenge our understanding of physics, but would dismantle the very idea of a physical location. The violation of Bell's inequality. For decades, the debate remained philosophical, until experiments transformed it into a matter of raw data, proving that no local hidden variables can account for the correlations we observe in the laboratory. In 1964, a physicist named John Stuart Bell devised a mathematical theorem that would finally put Einstein's spooky action to the test. He realized that if the world were truly local, if particles carried secret, predetermined instructions, as Einstein suspected, there was a strict limit to how often their behaviors could correlate. This limit is known as Bell's inequality. If measurements showed correlations stronger than this limit, then the concept of local realism would be mathematically impossible. The universe would be forced to reveal whether it was composed of independent things or an inseparable whole. When the experiments were finally conducted, using pairs of entangled photons sent in opposite directions, the results were unequivocal. The inequality was violated. The photons were correlating their states more frequently than was possible under any model of local, hidden reality. This was not a failure of the equipment or a statistical anomaly. It was a measurement of the fundamental architecture of space. The data proved that no underlying instruction manual exists within the particles. They do not decide their state until the moment of measurement, and yet the distant partner somehow reflects that choice instantaneously. This realization is quietly devastating to our understanding of causality. We are used to the idea that for A to affect B, something must travel between them, a wave, a particle, a signal. But in Bell's experiments, there is no signal. There is no time for a message to be sent, even at the speed of light. The correlation happens because the two particles are not actually two separate entities. They are a single phenomenon manifesting in two locations. The violation of Bell's inequality suggests that the distance between these particles is a superficial feature, a byproduct of our perspective, rather than a fundamental constraint of the universe. The implications of this measurement extend far beyond the laboratory. If local realism is false, then the properties of the physical world are not real in the way we traditionally define the word. We cannot say that a particle has a certain spin or position before we look at it. We cannot even say that the particles exist as distinct objects in space. Instead, we are looking at a reality where the very concept of location is secondary to the concept of information. The universe is not a collection of objects existing within space. It is a network of correlations that gives rise to the appearance of space. We must accept a conclusion that is deeply counterintuitive. The world does not exist in a definite state when we are not looking at it. This is no longer a philosophical speculation or a poetic metaphor. It is the result of rigorous, repeatable laboratory data. The realness we attribute to the world is a persistent illusion maintained by our lack of access to the quantum level. When we peel back the curtain of our daily experience,
we do not find a more solid foundation. We find a void of definite properties. A place where things only become real through the act of interaction. This discovery leaves us in a state of unresolved unease. We continue to live in a world that feels local, solid, and objective, yet we now possess the measurements that prove this feeling is a lie. The violation of Bell's inequality tells us that the universe is fundamentally non-local, meaning everything is connected in a way that bypasses the limits of time and space. We are living inside a projection, a macro-scale theater where the actors only take their places when the lights go up. The erasure of locality. The measurements confirm that two entities separated by vast distances can behave as a single unit, implying that the distance between them is an illusion generated by our scale of observation. In our daily experience, space is the primary divider. It is the void that keeps things apart. The vacuum that ensures an event in a distant galaxy has no immediate bearing on your life here on Earth. We define here specifically by its lack of there. However, the data from entanglement experiments forces a radical reassessment of this void. If two particles can coordinate their states instantaneously across any distance, then the space between them is not performing the function we thought it was. It is not a barrier. It is a secondary construct. To understand the erasure of locality, one must look at the mechanism of a non-local universe. In a local world, for information to travel from point A to point B, it must traverse every point in between. This is the logic of the field, the idea that influences ripple through space like waves in water. But in a non-local reality, the points in between are bypassed entirely. The correlation does not travel through space, it exists outside of it. This suggests that the three-dimensional volume we inhabit is not the fundamental level of reality. Instead, it is more like the surface of a pond, where two distant ripples might actually be caused by the same submerged object breaking the surface in two places. This realization dismantles our concept of scale. We assume that because we are large, we are made of many distinct parts distributed through space. But if locality is an illusion, then the distribution of matter is merely a descriptive tool, not a physical truth. At the fundamental level, the particles that compose your body, the air around you, and the furthest stars are not separated by distance in the way we perceive. They are part of a singular, contiguous informational state. The vastness of the cosmos, the billions of light years that seem to dwarf human existence, may be nothing more than a specific way of organizing data, a perspective necessitated by our biological limitations rather than a property of the universe itself. The unsettling implication is that motion and travel are also illusions. If there is no fundamental distance to overcome, then moving from one side of a room to the other is not a traversal of a physical vacuum, but a sequential update of your local coordinates within an informational field. We are like characters on a screen who believe they are walking across a vast landscape, unaware that the landscape is merely a set of pixels changing color in a fixed grid. The depth, the distance, and the time it takes to cross it are artifacts of the processing, not the hardware. This brings us to a conflict between our measurements and our intuition. We see a universe of expanding space and receding galaxies, yet our physics tells us that the foundation of this universe is a non-local unity. We are left to wonder why the illusion of locality is so persistent. Why does the universe go to such lengths to appear as though it is composed of separate parts, separated by vast reaches of nothingness?
The answer may lie in the fact that without the illusion of space, there can be no causality, no history, and no experience. To have a happening, you must have a where and a when. By erasing locality, we do not just lose our sense of place, we lose the framework that allows us to exist as distinct individuals. We are left standing in a reality that is essentially hollow. The space you see out of your window, stretching to the horizon and beyond to the stars, is not a vast container. It is a mathematical relationship. You are not a small thing in a large universe. You are a localized manifestation of a system that has no true edges and no true interior. The distance between you and the furthest reaches of the observable world is zero, masked only by the persistent, calculated delay of light. The fall of the objective observer. We traditionally view the scientist as a passive witness to an external world, but the data indicates that the act of measurement is not a report on a pre-existing state. It is the moment the state is defined. For centuries, the ideal of science was built upon the view from nowhere, the belief that a researcher could pull back a curtain and observe the clockwork of nature without disturbing its gears. This assumes a hard wall between the subject who perceives and the object that is perceived. We assumed that the universe had a definitive ledger of facts, and our role was simply to read them. However, as we pushed our inquiries into the foundational layers of matter, this wall collapsed. We discovered that the observer is not a bystander, but a participant, whose interaction forces the universe to make a choice. This shift is most visible in the way we now understand the state of a system before it is witnessed. In classical logic, if you have a closed box containing a ball, the ball is either on the left side or the right side. Your opening of the box reveals its location, but it does not create it. In the quantum reality that underpins our world, the ball is in a superposition of both states. It is only when the box is opened, when a measurement is made, that the wave function collapses into a single, localized reality. This implies that the world remains in a state of indefinite potential until an interaction occurs. The data does not suggest that we are merely ignorant of the state. It confirms that the state itself is not settled until the measurement is finalized. The implications for our concept of objectivity are catastrophic. If the properties of the universe are contingent upon the act of observation, then there is no true world independent of the observer. We are used to thinking of the Earth spinning and the stars burning, regardless of whether humans exist to see them. But if we take the results of our experiments to their logical conclusion, properties like position, momentum, and even existence are relative values that emerge only during an exchange of information. We are forced to ask, what is the universe doing when we are not looking? The mathematics suggests it is not a world of things at all, but a mathematical haze of probabilities, a cloud of maybes that only hardens into is when it is touched by a conscious or mechanical probe. This leads to a disturbing circularity in our understanding of existence. We are composed of atoms, yet those atoms require an observation to define their own states. This creates a chain of dependence that has no obvious beginning. If every physical system requires an external observer to collapse its possibilities into reality, then the universe itself appears to be a system that cannot exist without a witness. This is not a mystical claim, but a structural problem in the Copenhagen interpretation of physics. It suggests that the objective world we rely on is a secondary phenomenon,
a consensus reality created by the constant, overlapping observations of everything within it. We are left with a reality that is fundamentally shy. It refuses to commit to a definite form until it is cornered by a measurement. This shatters the comfort of the scientific method as a tool for discovering a pre-existing world. Instead, the method becomes a way of negotiating with a reality that is being generated in real time. The scientist is no longer a cartographer mapping a continent. They are more like a player in a video game, whose movement triggers the rendering of the terrain. The terrain was not there before the character turned their head. It was merely a set of instructions waiting to be executed. This realization leaves a heavy, unresolved tension in our perception of the everyday. You look at the objects in your room and realize that their objective presence is a result of a continuous, quadrillion-fold collapse of probability happening every nanosecond. The world feels solid and reliable only because the scale of our observation is too coarse to see the flickering uncertainty beneath it. We are not living in a world of objects, but in a world of responses. The universe is a mirror that only provides an image when we stand before it, leaving us to wonder what remains in the dark when we finally turn away. The Kochen-Specker theorem. This mathematical certainty demonstrates that the properties of a system are inextricably linked to the context in which they are measured, meaning an object cannot be said to have a definite value in isolation. In our standard view of the world, we assume that a property, such as the color of an apple or the speed of a car, belongs to the object itself. We believe that these values are non-contextual, meaning they remain the same regardless of how we choose to look at them or what other questions we ask about the system at the same time. The Kochen-Specker theorem, proven in 1967, systematically destroys this assumption. It provides a rigorous proof that for any quantum system, it is impossible to assign fixed, pre-existing values to all its observable properties in a way that is independent of the measurement context. To grasp the weight of this, imagine a collection of light switches in a room. In a classical, real world, each switch is either on or off, and its state is a fixed fact. You could walk into the room and flip switch A, and the result would be independent of whether you also decided to flip switch B or switch C. The Kochen-Specker theorem reveals that the universe does not work this way. Instead, the value of switch A literally changes depending on which other switches you are looking at simultaneously. The property does not live in the object. It lives in the relationship between the object and the specific set of questions you are asking it. This is known as contextuality, and it implies that there is no true state of an object that exists in a vacuum. This theorem moves beyond the uncertainty of not knowing a value. It proves the non-existence of a value. It suggests that the universe is not a collection of answers waiting to be found, but a series of responses that are generated based on the configuration of the observer. If you measure a particle's property in context X, you get result A. If you measure that same property in context Y, the very nature of what you are measuring has shifted. There is no underlying real value that stays constant across both scenarios. This leaves us with a reality that is fundamentally fragmented. The thing we thought we were studying has no identity outside of the experiment. This creates a profound logical crisis. If an object's properties depend on the context of their measurement, then the idea of an objective physical world becomes a contradiction. We rely on the consistency of the world to build our houses, our bridges, and our sense of self. But the Kochen-Specker theorem informs us that this consistency is a macro-scale illusion. At the foundational level, the world is a shifting mosaic where facts are only facts relative to the specific way they are being accessed. An atom does not have a spin in the way a ball has a color. It has a potential for spin that only resolves into a specific value when placed within a specific comparative framework. The unsettling conclusion is that the universe is not made of stuff with traits. It is made of events. We are used to a noun-based reality where things have attributes. This theorem forces us into a verb-based reality where interactions create the attributes we previously thought were permanent. If you were to stop measuring, stop interacting, and stop contextualizing, the properties of the universe would not just become hidden, they would cease to be. The world is a performance that requires a specific stage and a specific audience to manifest any qualities at all. We find ourselves in a universe that is fundamentally non-intrinsic. Nothing exists in its own right. Everything you perceive as a stable, physical fact is actually a conditional response. This realization leaves you in a reality that is far more fragile than it appears. The solidity of your environment is not a product of the things within it, but a product of the rigid, consistent contexts in which those things are placed. If the context were to shift, the very properties of the matter around you would dissolve, revealing that beneath the surface of our perceived reality, there is no solid ground, only a web of mathematical dependencies. Delayed choice and the rewriting of history. When we observe a photon's path after it has already traveled, the result dictates the history it took, suggesting that the past is not a fixed record, but a set of possibilities waiting for a present interaction to solidify. This concept, famously proposed by physicist John Wheeler as the delayed choice experiment, challenges our most basic understanding of causality. We operate under the assumption that the arrow of time is absolute, that an event occurs, is recorded by the universe, and becomes an immutable part of the past. However, the data reveals that the nature of a past event can remain undecided until a measurement is made in the present. If you choose to measure a particle as a wave, it has always been a wave. If you choose to measure it as a particle, its entire history is retroactively adjusted to reflect that path. This is not a matter of changing the past in the sense of science fiction, but rather a realization that the past does not exist in a definite state until it is connected to a conscious or mechanical observer. In Wheeler's cosmic version of the experiment, light from a distant quasar travels for billions of years before reaching Earth. During its journey, it encounters a galaxy that acts as a gravitational lens, bending the light around it. The light can take two different paths to reach us. According to the laws of quantum mechanics, until we decide how to measure that light, it has effectively taken both paths. The choice we make today, at a telescope in the 21st century, determines which path the photon took billions of years ago. The logical consequence is that the history of the universe is not a finished book, but a series of pages that are being written as they are read. We assume that the fossils in the ground, the light from distant stars, and the geological scars on the Earth are evidence of a fixed timeline that preceded us. But the delayed choice measurements suggest that these records are merely present-day observations that force a specific past into existence. The universe appears to be a participatory system, where the present moment reaches back into the abyss of time to solidify the events that led to it. If no measurement is ever made,
that history remains a blur of conflicting possibilities. This creates a profound sense of unease regarding the reliability of our own existence. If the past is contingent upon the present, then the foundation upon which we stand is not as solid as we perceive. We view ourselves as the end product of a long, linear chain of cause and effect, yet the physics implies that the chain is only linked when we look at it. This retrocausal aspect of reality suggests that information is the primary driver of time. The universe does not simply happen. It is refined through the process of information gathering. We are not just living in the present. We are constantly, unconsciously, finalizing the past. The mechanism behind this is the wave function, which encompasses all potential histories of a system. Until a measurement occurs, all these histories are equally real in a mathematical sense. When we perform a delayed choice experiment, we are essentially selecting one of these mathematical threads and promoting it to the status of physical reality. The other threads, the paths not taken, do not just vanish. They are rendered as having never happened at all. This leaves us in a world that is essentially a curated selection of events, a thin sliver of certainty carved out of a vast ocean of potentiality. We are left with a reality that is fundamentally untethered from a fixed timeline. The reassuring sequence of before and after is a local experience, a biological filter that allows us to navigate a world that is, at its core, timeless and indeterminate. When you look at the stars tonight, you are not just seeing light from the past. You are participating in the finalization of a history that has been waiting for eons for a witness. The past is not behind us. It is waiting for us to decide what it was. The quantum eraser experiment. By manipulating information about a particle's path after it has been detected, we can restore an interference pattern that had seemingly vanished, implying that information, not matter, is the fundamental currency of existence. This experiment is perhaps the most unsettling refinement of the double-slit setup. In a standard quantum experiment, if we gain which path information, knowledge of which specific slit a particle passed through, the interference pattern disappears and the particles behave like solid little rocks. The mere availability of information destroys the wave-like behavior of reality. However, the quantum eraser takes this a step further. If we take that gathered information and erase it so that it can never be known by any observer, the interference pattern reappears. The physical system knows that the information is gone, and it reverts to a state of wave-like probability. What makes this particularly disturbing is the timing. In a delayed choice quantum eraser, the erasure of information can happen after the particle has already hit the detection screen. The particle lands on the sensor as a single localized dot, the behavior of a solid object. But when the related information about its path is later destroyed, the collective pattern of these dots shifts to form an interference pattern. It is as if the particle's behavior in the past is dictated by the availability of information in the future. This suggests that the universe does not care about the physical movement of stuff through space. It cares only about the logical consistency of what can be known. We often think of information as something we write down in books or store on hard drives, a secondary description of a primary physical world. But the quantum eraser implies the inverse. Information appears to be the primary layer,
and the physical world is merely a manifestation of that data. If the information about a path exists, the universe must render a specific, particle-like reality to remain consistent. If that information is deleted, the universe unlocks that constraint, allowing the system to exist as a wave of possibilities once again. Matter, in this context, is not a solid foundation, but a decorative feature of an underlying informational architecture. This realization forces us to confront the possibility that the solidity of the world is a byproduct of the sheer amount of information being leaked into the environment. Every time a photon bounces off a surface or an atom bumps into another, which path information is being recorded by the universe? This constant exchange of data, decoherence, is what keeps the world looking real and solid to our eyes. We are living in a high-resolution environment only because the information is so densely interwoven that the underlying wave-like nature of reality is erased by the noise of constant measurement. The implications of the quantum erasure suggest a reality that is fundamentally economical. The universe only bothers to render a definite physical state when the information demands it. If no one can know which path was taken, the universe remains in a state of flux. This is not a limitation of our consciousness, but a rule of the system itself. We are trapped in a reality that behaves exactly like a simulated environment that only renders the details of a room when the player looks at them, optimizing its resources by keeping everything else in a state of low-resolution probability. Ultimately, the quantum erasure leaves us with a profound sense of hollowness. If you could somehow isolate a large object, or even yourself, from all informational exchange with the outside world, you would cease to be a solid entity with a definite location. You would dissolve into a wave of probability, existing everywhere and nowhere at once, until a single bit of information was recovered to pull you back into the real world. We are held in place not by gravity or atoms, but by the persistent, unerasable data of our existence. The holographic principle. Black hole thermodynamics suggest that the entire information content of a three-dimensional volume can be perfectly described by the data on its two-dimensional boundary, rendering the depth of your world a projection. This principle emerged not from speculative philosophy, but from a crisis in how we calculate the limits of matter. When an object falls into a black hole, it appears to be lost forever. However, physics dictates that information cannot be destroyed. To resolve this, researchers like Stephen Hawking and Leonard Susskind discovered that as an object crosses the event horizon, its data is not vanished. Instead, it is smeared across the two-dimensional surface of the hole. The amount of information the black hole can hold is proportional to its surface area, not its volume. This was the first hint that the three-dimensional inside of a system might be an illusion generated by a two-dimensional outside. In your daily life, you perceive the world as a vast container. You see rooms with volume, cities with depth, and a universe that stretches billions of light-years in every direction. You assume that, to describe a region of space, you must account for everything inside that volume. But the holographic principle suggests that this is a mathematical redundancy. If the information of a volume can be fully contained on its boundary, then the third dimension, the depth you move through, may not be a fundamental property of that universe. It is more akin to a hologram on a credit card, a flat, two-dimensional surface that, when illuminated correctly, produces the vivid, convincing image of a three-dimensional object. This realization forces a terrifying inversion of our sense of reality.
We traditionally believe that the real things are the solid objects we can touch, and the information we use to describe them is secondary. The holographic principle implies the opposite. The real data exists on a distant two-dimensional boundary, and you are the projection. Everything you experience, the weight of your body, the texture of the ground, the distance between the stars, is a manifestation of bits of information interacting on a surface that you can neither see nor reach. We are not the inhabitants of a 3D world. We are the shadows cast by a 2D reality. The mechanism behind this is rooted in the Bekenstein bound, which sets a maximum limit on the amount of information that can exist within any given region of space. When you attempt to pack too much information, too much matter or energy into a finite volume, the region collapses into a black hole. At that limit, the volume vanishes, and only the surface remains to carry the data. If the limit of information is determined by area, then the universe is effectively a two-dimensional system masquerading as a three-dimensional one. This means that at the most fundamental level, the empty space you see between objects is not empty. It is simply part of the projection that hasn't been encoded with data. This perspective dismantles the idea of locality even further. If you and a distant star are both projections from the same two-dimensional surface, then your distance from that star is merely a specific configuration of pixels on the boundary. In the underlying reality, you and the star may be adjacent. The sensation of travel and the vastness of the cosmos are just ways our brains interpret the complex interference patterns of the holographic data. We are living inside a decoded signal, mistaking the playback for the source. The unease comes from the lack of a center. If our world is a projection, where is the projector? The mathematics does not provide a comfortable answer. It suggests that the boundary and the projection are mathematically equivalent, two ways of describing the same set of information. There is no more real version of you. There is only the data and the experience of that data. We are trapped in a feedback loop, where the three-dimensional world feels solid only because we are part of the projection ourselves. We cannot step outside the hologram to see the surface, leaving us to navigate a world of depth that our own physics tells us is a flat, flickering facade. The ADS/CFT correspondence. Mathematical models now show a direct duality between a universe with gravity and a flat system without it, leading to the unsettling possibility that our three-dimensional reality is a shadow of a lower dimensional source. This discovery, formulated by Juan Maldacena in 1997, is known as anti-de Sitter/conformal field theory correspondence. It provides a mathematical bridge between two seemingly incompatible worlds, a multidimensional universe governed by Einstein's equations of gravity, and a lower dimensional boundary governed purely by quantum field theory, without any gravity at all. The correspondence proves that these two descriptions are mathematically identical. Everything that happens in the bulk of the higher dimensional space, the movements of planets, the falling of rain, the passage of time, can be perfectly mapped to the interactions of quantum particles on a distant, flat surface. In your daily existence, you perceive gravity as a fundamental force that pulls you toward the Earth and keeps the Moon in its orbit. You experience the three dimensions of space as the primary theater of action. However, the ADS/CFT correspondence suggests that gravity itself may not be a fundamental force, but rather an emergent phenomenon. It is a collective effect, similar to how the concept of temperature emerges from the frantic movement of millions of individual molecules. If gravity is emergent, then the space it acts within is also emergent. This implies that the three-dimensional world you inhabit is a secondary construction, a complex organizational layer derived from simpler, non-gravitational data existing on a lower dimensional boundary. The logic of this duality is precise and unforgiving. If two different mathematical systems describe the same reality perfectly, then the distinction between them is merely a matter of perspective. One side of the duality describes a universe with depth and gravity. The other describes a flat surface with no gravity. If the flat surface is the more fundamental source code, then your experience of falling, of weight, and of distance is a translation of data. You are essentially living inside a mathematical equivalence where the interior of the universe is a projection of the exterior boundary. This leaves us with a reality that has no independent core. It is a shadow play where the light, the screen, and the actors are all part of the same flattened equation. This leads to a profound sense of displacement. We assume that the center of the room, the center of the earth, and the center of our own bodies are the most real points in space. But the correspondence suggests that the most fundamental stuff of the universe is actually located at the furthest possible edge. The boundary is where the real physics happens. The bulk, the space where you are currently standing, is a derivative. It is as if you discovered that your entire life was not taking place inside a house, but was instead a high-fidelity reflection occurring on the surface of a bubble. The interior is empty of fundamental laws. It only possesses the laws that have filtered in from the surface. The mechanism of this translation is built on entanglement. The way the particles on the boundary are linked to one another determines the geometry of the space in the interior. If the entanglement on the surface changes, the physical distance between two objects in your three-dimensional world changes. This reinforces the idea that space is not a vacuum waiting to be filled, but a fabric that is woven or unraveled by information. We are observing a universe that is fundamentally thin. The depth we see is a trick of the data, a way for the system to organize vast amounts of quantum information into a coherent, navigable map. We are left navigating a world that lacks intrinsic volume. The three-dimensional reality you trust is a convenient representation of a reality that is far more alien and far less spacious than it appears. Every time you move through a room, you are moving through a projection. Every time you feel the pull of the earth, you are feeling the mathematical consequence of a boundary you can never touch. The ADS/CFT correspondence doesn't just suggest that reality is a hologram. It provides the rigorous, inescapable proof that the world you see is a shadow of a truth that exists elsewhere. Entanglement as the fabric of spacetime. We once thought of spacetime as a stage upon which particles act, but current research suggests that the geometry of space itself is woven together by the entanglement of quantum bits. In the classical view, space is a passive container, an empty void that exists whether or not matter is present to occupy it. We imagined that if we were to remove every atom and every photon from the universe, we would be left with a smooth, continuous fabric of four-dimensional spacetime. However, recent developments in theoretical physics, specifically the ER equals EPR conjecture, suggest that this void is not a primary entity. Instead, space is an emergent property, a manifestation of the quantum connections between the most fundamental units of information. The mechanism behind this is rooted in the way quantum states are linked. When two particles are entangled, they share a single existence that transcends distance. Physicists now suspect that these threads of entanglement are the very stitches that hold the universe together. If you were to systematically break the entanglement between all the particles in a region of space, the geometry of that region would collapse. The distance between points would cease to have meaning, and the fabric would unravel into a disjointed collection of data points with no spatial relationship to one another. Space, therefore, is not the thing that contains entanglement. It is the thing that entanglement creates. This realization shifts our understanding of the universe from a material one to an informational one. We are used to thinking of closeness as a physical measurement, the number of meters or light years between two coordinates. But if space-time is woven from entanglement, then closeness is simply a measure of how strongly two systems are quantum mechanically correlated. Two objects appear to be near each other because they are highly entangled. They appear far apart because their connection is weak. The vast distances of the intergalactic medium are not empty stretches of nothing, but areas of low entanglement density. The implications of this are quietly unsettling. If the geometry of your world is maintained by a web of quantum links, then the solidity of the space you move through is contingent upon the persistence of those links. We perceive a stable, unchanging background because the sheer number of entangled bits is so vast that the overall structure remains consistent. But at the smallest scales, the Planck scale, the fabric of space likely resembles a chaotic, bubbling foam of connections forming and breaking. Your sense of a smooth, continuous reality is a macro-scale illusion, a statistical average of a microscopic storm of information. Furthermore, this model suggests that gravity is not a force pulling on matter, but a result of the way entanglement curves the informational manifold. When mass energy is present, it alters the entanglement patterns of the surrounding vacuum, and we perceive this change as the curvature of spacetime. We are essentially living inside a giant, self-organizing quantum computer where the geometry of the world is just the output of the system's internal correlations. The floor beneath you, the sky above, and the gap between your hands are all products of a deeper, invisible connectivity that ignores the very concept of separation. We are left with the conclusion that the universe is not a place where things happen, but a state of being where things are connected. The stage of spacetime is not a foundation, it is a symptom. When you look out at the horizon, you are not looking at the far reaches of a physical container. You are looking at the limits of a specific network of information. If the entanglement were to vanish, the universe would not become an empty room. It would cease to be a room at all, leaving behind a reality that is fundamentally spaceless, timeless, and utterly incomprehensible to a mind designed to navigate 3 dimensions. The vanishing of space. If entanglement is the source of distance, then here and there are merely descriptions of how closely correlated 2 pieces of information are, rather than physical coordinates in a void. We have long operated under the assumption that space is the fundamental substrate of the universe, a vast, empty theater that exists prior to the matter placed within it. We think of a vacuum as a literal nothingness that separates some things. However, modern physics suggests that this nothingness is an elaborate deception. If you remove the quantum correlations that link one point to another, the distance between them does not become infinite. It simply ceases to exist. Space is not a container. It is a manifestation of how information is networked. This brings us to a conclusion that is difficult to process. The 3-dimensional world you navigate is a low-resolution representation of a higher-dimensional connectivity. In your daily life, you experience the difficulty of travel. To move from your home to a distant city requires time and energy because you must traverse every intervening millimeter of the physical void. But if space is emergent from entanglement, then that traversal is actually a process of navigating a data structure. Two points are far apart only because their quantum states share very little mutual information. The vast, cold reaches between galaxies are not empty volumes, but regions where the density of entanglement is at its thinnest. The mechanism of this vanishing space can be likened to the way a computer handles a virtual environment. In a game, two objects might appear miles apart on the screen, but in the computer's memory are merely bits of data sitting side by side on a silicon chip. The distance is a programmed constraint, a rule of the simulation designed to provide a coherent experience for the user. In our universe, the rules are the laws of quantum mechanics. When entanglement is high, the geometry is tight and objects are near. When entanglement is low, the geometry stretches. If the entanglement were to be severed entirely, the very concept of between would vanish, leaving a reality where everything is effectively on top of everything else. This realization forces us to confront the hollowness of the cosmos. If space is not a physical thing, then the expansion of the universe, the observation that distant galaxies are moving away from us, is not a literal stretching of a fabric. Instead, it is a global decoherence, a systematic thinning of the entanglement density across the system. The universe is not getting larger in the sense of a balloon inflating. It is becoming more disjointed. The informational links that hold the here and there together are fraying, creating the illusion of increasing distance where there is only a decrease in correlation. This leads to a quiet, existential unease. If the space between your hands is nothing more than a specific density of quantum bits, then your own physical extent is a fragile calculation. You feel solid and localized because you are a highly correlated cluster of information. But there is no void protecting you from the rest of the universe, and there is no distance truly separating you from the furthest star. We are suspended in a web of dependencies. The moment those dependencies shift, the geometry of our reality shifts with them. We are not moving through space, we are being rendered by it. Ultimately, the vanishing of space suggests that the universe is fundamentally non-spatial. Where is a concept that only exists for observers trapped within the network, outside of the collective entanglement of the cosmos. There are no coordinates, no directions, and no volumes. There is only a sea of information, existing in a state that our three-dimensional brains are not equipped to visualize. We are looking at a map and mistaking it for the territory, unaware that the paper it is printed on is an illusion of the ink itself. Wigner's friend and multiple truths. Recent laboratory scales have allowed us to perform experiments where two observers see two different, equally valid realities, suggesting that there is no single, objective world that contains us both. This concept stems from a thought experiment proposed by Eugene Wigner in 1961, which has recently been realized using photons in a laboratory setting. In this scenario, one observer, the friend, is inside a closed laboratory performing a quantum measurement on a particle. From the friend's perspective, the measurement is a definitive event. The wave function has collapsed, and a single objective fact has been established. However, for a second observer, Wigner, standing outside the laboratory, the entire room and everyone in it remain in a state of superposition. To Wigner, the friend has not measured a fact, but has instead become entangled with the particle, existing in a ghostly blur of multiple possible outcomes.
The conflict here is not a matter of one person being right and the other being wrong. According to the laws of quantum mechanics, both observers are entirely correct within their own frames of reference. This is known as a subjective or relational reality. The data suggests that there is no overarching God's eye view of the universe that can reconcile these two accounts into a single, consistent story. If you were the friend, you would swear the particle was spinning up. If you were Wigner, you would correctly calculate that the friend is in a state of both up and down simultaneously. The universe appears to lack a central ledger of truth, allowing for contradictory facts to coexist as long as they are isolated from one another. This realization dismantles the notion of a shared, objective world. We navigate our lives under the assumption that if we both look at the same clock, we are seeing the same time because the clock exists in a specific state, independent of us. But the Wigner's friend experiments indicate that the state of the clock is not a fixed property of the clock itself. It is a property of the relationship between the clock and the person looking at it. If you and another person are not sufficiently entangled, you may effectively be living in two different versions of the present. The world is not a single, solid stage, but a fragmented collection of personal bubbles of reality that only align when information is exchanged. The mechanism that prevents us from noticing this in our daily lives is decoherence, the constant, chaotic leaking of information into the environment. When trillions of atoms interact, measure each other so frequently that the contradictory realities are forced to align, creating the illusion of a single objective consensus. But this consensus is a statistical byproduct, not a fundamental requirement of the universe. In the controlled silence of a quantum laboratory, that consensus vanishes. We are left with the evidence that two people can witness the same event and come away with two different, mathematically perfect truths that can never be fully merged. This leads to a chilling conclusion about the nature of social and physical reality. If there is no objective world, then facts are merely localized agreements. We are used to the idea that truth is something we discover, but the data suggests that truth is something we produce through our interactions. Beyond the reach of our immediate measurements, the universe remains a vast, undecided soup of contradictions. There is no way things are when no one is looking, and there is no guarantee that the way things are for you is the way they are for anyone else. We are left standing in a reality that is fundamentally lonely. We believe we are sharing a world with others, but we may only be sharing a set of correlations. The person standing next to you is navigating their own version of the universe, and while your accounts may match, the underlying physics admits that they do not have to. The objective reality we cling to is a fragile, macroscopic treaty, a temporary truce between a trillion different quantum possibilities that could, at any moment, diverge. The relational universe. If reality depends on the observer, then the universe is not a collection of things, but a web of relations, where an object only gains properties relative to another object. This perspective, known as relational quantum mechanics, suggests that our search for the fundamental building blocks of matter is fundamentally misguided. We have spent centuries trying to identify the smallest, most irreducible stuff, the atoms, the quarks, the strings. But the data indicates that these entities do not have any intrinsic properties of their own. A particle does not have a position. It has a position only relative to the detector that clicks when it passes by.
It does not have a velocity. It has a velocity only relative to another object in its environment. Outside of these interactions, the particle is not a thing with missing data. It is a void of properties. This shifts the focus of physics from the study of objects to the study of information exchange. In a relational universe, the concept of an absolute state is discarded. We are used to thinking that if we could step outside the universe, we would see everything in its true, final state. But the relational model proves that such a viewpoint is a logical impossibility. There is no outside. Every description of a system is made from the perspective of another system. This means that reality is not a single, monolithic structure, but a vast, interconnected network of perspectives. The world, as you know it, is the sum of these relations, a shifting mosaic of interactions that never settles into a permanent, objective form. The mechanism of this relational reality can be seen in the way we define physical constants. We measure the mass of an electron or the charge of a proton, but these values only manifest during an interaction. If an electron were to exist in a total vacuum, completely isolated from any other field or particle, it would effectively have no measurable qualities. It is the interaction, the relation, that calls the property into existence. This implies that the universe is not a container filled with objects, but a series of events. We perceive a table as a solid object, but what we are actually experiencing is a dense cluster of electromagnetic relations between the atoms of the table and the atoms of our hand. The tableness is not in the wood, it is in the exchange. This realization leads to a profound sense of ontological instability. If things only exist in relation to other things, then what is at the bottom of the chain? If A exists because of B, and B exists because of C, we are left with a recursive loop that never anchors itself in a real foundation. This suggests that at the core of our reality, there is nothing. Not a vacuum, not a void, but a lack of inherent being. We are living in a world of mirrors, where every image is a reflection of another reflection, with no original object to be found. The solidity of your surroundings is a result of the sheer complexity of these reflections, a statistical thickness that obscures the underlying hollowness of the system. The implications for our sense of self are equally unsettling. If the universe is relational, then you are not a fixed entity moving through a world of other fixed entities. You are a localized nexus of relations. Your body, your thoughts, and your perceptions are a specific set of interactions occurring within the wider network of the cosmos. If those relations were to be severed, there would be no essence of you left behind. You exist only because the universe is constantly measuring you, and you are constantly measuring it back. We are participants in a recursive observation loop that sustains the appearance of existence through the sheer persistence of the exchange. We are left with a universe that is fundamentally empty of independent objects. The reassuring world of nouns, people, places, things, is a linguistic layer we have draped over a reality of verbs. There is only the happening, the correlating, and the measuring. When you look at the stars, you are not looking at distant objects across a void. You are experiencing a long-distance relationship between your retina and a distant fusion process. The thing is the relation itself.
The terrifying truth of the relational universe is that if the interactions were to stop, the world would not just go dark.
It would cease to have ever been there at all.
The computational limit of matter.
Every piece of matter occupies space and possesses energy, but it also represents a finite amount of information, suggesting the universe has a maximum resolution beyond which nothing exists. In classical thought, we imagined that space and matter were infinitely divisible. You could, in theory, take a centimeter of space and divide it into millimeters, micrometers, and so on, forever. But the laws of thermodynamics and quantum mechanics have revealed a hard floor to this divisibility. This is known as the Bekenstein bound, which dictates that a finite region of space can only contain a finite amount of information. If you attempt to cram more data, more reality, into that space, the region will collapse into a black hole. This implies that the universe is not a continuous, infinite canvas, but a system with a specific, pixelated limit. This realization shifts our understanding of an object from a physical substance to a data set. A single hydrogen atom is not just a collection of a proton and an electron. It is a specific configuration of quantum states that requires a measurable amount of information to describe. When we scale this up to the macroscopic world, we find that the solidity of the objects around you is actually a measure of informational density. Your body, your chair, and the device you are holding are all occupying portions of the universe's bandwidth. If the universe has a finite capacity for information, then every physical process is essentially a calculation, and matter is the hardware upon which that calculation is performed. The mechanism of this limit is defined by the Planck length, the smallest possible unit of distance. At this scale, approximately 10 to the power of minus 35 meters, the very concepts of here and there break down into a chaotic foam. Just as a digital image reveals its underlying pixels when zoomed in too far, the fabric of reality reveals its discrete nature at the Planck scale. There is no space between these units, and there is no smaller than this limit. This suggests that the universe has a built-in resolution, a maximum frame rate and pixel density, beyond which the rendering of reality simply stops. We are living in a world that is not smooth, but granular. The implications of a pixelated reality are deeply unsettling. In a truly continuous universe, an object could move with infinite precision. But in a granular universe, motion must occur in discrete jumps, flickering from one Planck unit to the next. We do not perceive these jumps because our biological sensors are far too slow, much like we do not see the individual frames of a film moving at 60 frames per second. However, the data confirms that these limits exist. If the universe is finite in its information capacity, it behaves less like a physical void and more like a computational output. This raises the question of what happens to the data of our lives when the system reaches its local limit. This leads to the concept of informational saturation. If a region of space is filled with the maximum amount of information it can hold, it becomes a holographic surface, as we explored previously. But even before that extreme is reached, the finite nature of matter implies that the universe is economical. It does not store information it does not need. When a particle is not being interacted with, the universe does not bother to calculate its specific properties, leaving them in a state of probability. The universe only computes the definite state of an object when a measurement forces the system to update its ledger. We are living in a reality that manages its resources with the cold efficiency of an algorithm. Ultimately, the computational limit of matter suggests that reality is not an inherent fact,
but a processed result. The weight and mass you feel are the sensory interpretations of bits of information being
processed at the universal limit. If you were to look close enough at the fabric of your own existence, you would not find more stuff. You would find the edge of the code. We are the inhabitants of a system that has a maximum resolution, a ceiling on how much reality it can actually manifest at once. Beyond that ceiling, there is not just darkness, there is nothing at all. The simulation hypothesis as a logical constraint. This is not a suggestion of a digital creator, but a recognition that a universe defined by discrete information and mathematical laws is indistinguishable from a calculated output. When we speak of the simulation hypothesis in a scientific context, we are moved beyond the pop culture imagery of the Matrix and into the territory of algorithmic information theory. If the universe possesses a maximum resolution, a finite speed for information transfer, and a quantized structure for energy and time, it begins to look less like an organic, infinite mystery and more like a system governed by a finite state machine. The laws of physics are not just descriptions of how things happen, they are the constraints of the system's architecture. In this view, the real is simply that which is being currently computed by the laws of the cosmos. The mechanism of this constraint is found in the way physical laws function as code. Consider the fundamental constants of nature: the gravitational constant, the speed of light, and the Planck constant. These are not merely arbitrary numbers. They are the hard-coded parameters that determine the behavior of every interaction. If these values were different, the output of the universe, stars, atoms, and life, would not exist. The fact that our reality is governed by discrete mathematical rules suggests that the universe does not have the freedom we once attributed to it. It is bound by a logic that is fundamentally computational. Every particle collision is a solved equation. Every chemical bond is a logical gate being satisfied. This realization forces us to confront the efficiency of reality. In computer science, an efficient simulation does not render what is not being seen. It uses lazy evaluation to save processing power. We see a mirror of this in the quantum world through wave function collapse. As we have observed, a particle remains in a state of probability until a measurement occurs. This is functionally identical to a system that only calculates the specific position of an object when that data is requested by the program. The universe behaves as though it is conserving its computational resources, only hardening into a definite state when it is absolutely necessary to maintain the consistency of the internal logic. The implications are quietly disturbing for our sense of autonomy. If the universe is a calculated output, then every event in your life, from the firing of a neuron to the movement of a planet, is a step in a vast, unfolding algorithm. We perceive choice and randomness, but these may be artifacts of our inability to see the underlying code. The randomness of quantum mechanics might not be true chaos, but simply the result of a pseudo-random number generator that is too complex for us to reverse engineer. We are moving within a set of logical constraints that were established at the moment of the Big Bang, which itself looks increasingly like the initialization of a system. Furthermore, the simulation hypothesis, as a logical constraint, implies that there is a base level to reality that we can never observe. If we are the output of a mathematical system, we are trapped within the logic of that system. Just as a character in a computer game cannot use their physical strength to break the monitor they are displayed on, we cannot use our physical laws to peer behind the curtain of the laws themselves. We are limited by the bit rate of our own existence. The terrifying aspect of this is not that someone is watching us, but that there might be nothing to watch, just a self-sustaining calculation that exists because its equations are solvable. We are left in a universe that is mathematically perfect, but ontologically hollow. Our existence is a persistent, high-fidelity calculation that provides the sensation of solidity, time, and space. But if the calculation were to reach its final step, or if the underlying logic were to encounter an unresolvable error, the world would not break, it would simply stop being rendered. We are the variables in a cosmic function, searching for meaning in a world where the only truth is the cold, unwavering consistency of the math. The fine-tuning of mathematical constants. The laws governing your existence are so precisely calibrated that a deviation of a fraction of a percent would result in a universe incapable of structure, suggesting a narrow corridor of viable reality. We often take for granted that the stars shine, that atoms hold together, and that complex chemistry allows for the emergence of life. However, these outcomes are not guaranteed by the mere existence of physics. They are the result of specific, seemingly arbitrary numbers known as fundamental constants. If the strong nuclear force, the glue of the atomic nucleus, were only 2% stronger, hydrogen would not exist, and the stars would have never ignited. If it were slightly weaker, no element heavier than hydrogen could ever form. We find ourselves in a universe that appears to have been tuned to a razor's edge, where the slightest tremor in the underlying mathematics would result in a sterile, featureless void. This precision extends to the very expansion of space itself. The cosmological constant, which represents the energy density of empty space, is fine-tuned to an almost inconceivable degree. If this value were larger by 1 part in 10,120, the universe would have expanded so rapidly after the Big Bang that matter could never have clumped together to form galaxies or planets. If it were slightly smaller, the universe would have collapsed back in on itself long before the first star could form. This degree of accuracy is comparable to firing a needle from one side of the observable universe and hitting a target 1 millimeter wide on the other side. The data does not suggest a robust, flexible system. It suggests a precarious one, where reality is a statistical miracle. The mechanism behind this tuning remains one of the greatest unsettled questions in cosmology. We are faced with two equally unsettling possibilities. The first is the anthropic principle, which suggests that we only observe these values because, in any universe where they were different, we would not be here to measure them. This implies a multiverse, an infinite sea of failed, chaotic, or empty universes, with ours being a rare, lucky pocket of stability. In this scenario, your existence is not the result of a grand design, but a mathematical necessity born from an infinite number of casualties. You are a survivor in a graveyard of dead realities. The second possibility is that these constants are not arbitrary, but are fixed by a deeper yet undiscovered law of nature. This would mean that the universe must be this way. However, this offers no comfort, as it implies a rigid, deterministic system that functions like a machine with only one possible setting. Whether the result of luck or necessity, the fine-tuning of the constants reveals that the solidity of your world is dependent on a series of numbers that could have been anything else. We are supported by a scaffolding of digits that has no obvious reason for being so precise. Yet, without that precision, the concept of you vanishes instantly. This brings us to the realization that reality is a narrow-band phenomenon. We inhabit a tiny sliver of the possible ways a universe could exist. Most mathematical configurations of physics do not produce light, solid matter, or time as we understand it. They produce nothing in 1,000 different ways. By measuring these constants, we are acknowledging that our reality is an anomaly. We are living in the only version of the calculation that doesn't result in an error or a blank screen. This creates a sense of profound fragility. The ground beneath your feet is held together by a mathematical equilibrium so delicate that it defies conventional probability. We are left looking at a universe that is functionally a Goldilocks reality. Not too fast, not too slow, not too strong, not too weak. But this balance is not a sign of safety. It is a reminder that the parameters of your existence are external to you. You do not control the code that allows your atoms to exist. You are merely a byproduct of it. The fine-tuning of the constants suggests that the universe is a high-stakes lottery, and the fact that you are here to observe it does not change the fact that the odds were stacked almost infinitely against them. Existence of anything at all. The problem of Boltzmann brains. In an infinite or long-lived universe, the likelihood of a fully formed consciousness briefly flickering into existence via random fluctuation is higher than the evolution of a stable biological world. This unsettling paradox, named after the physicist Ludwig Boltzmann, arises from the second law of thermodynamics and the nature of entropy. We assume that our presence in this room, surrounded by a coherent history and a vast, structured cosmos, is the result of billions of years of gradual evolution following a low-entropy Big Bang. However, statistics suggest a much simpler path to consciousness. It is mathematically more probable for a single brain, complete with false memories of a life and a world, to spontaneously form out of the vacuum due to a rare thermal fluctuation than it is for an entire universe to maintain the order necessary for biological life to emerge over eons. To understand the mechanism of this fluctuation, one must look at the behavior of particles over vast timescales. In a universe that reaches a state of high entropy, often called heat death, matter is spread thin and energy is uniform. Yet, in an infinite amount of time, random collisions will eventually occur. Most of these collisions produce nothing of interest, but occasionally they will form an atom, then a molecule, and eventually a complex structure. Statistically, the simplest structure capable of hosting a conscious thought, a Boltzmann brain, requires far less luck and far less order to assemble than a trillion-star galaxy. If the universe lasts forever, these fleeting, lonely observers will outnumber biological observers by a factor of trillions. This creates a crisis of observational integrity. If you are a conscious observer, and the vast majority of observers in the history of the cosmos are Boltzmann brains, then the probability that you are a real biological entity is effectively zero. You feel the weight of your body and remember your childhood. But in a fluctuating universe, those sensations and memories are simply the configuration of the atoms that make up your fleeting brain. They are not evidence of a past. They are the noise of the present. The moment you finish this thought, the fluctuation may end, and the atoms of your mind will dissolve back into the chaotic void from which they momentarily emerged. The implication is that our scientific models may be self-undermining. We use our observations of the stars and the laws of physics to build a history of the universe. But if we are Boltzmann brains, our observations are hallucinations produced by a random arrangement of matter. The very data we use to conclude that the universe is old and vast would be a false input. We are trapped in a logical circle, where the more we rely on our perception of a stable reality, the more the statistics of an infinite universe suggest that our perception is a localized fluke. Reality you see out the window is not a massive, enduring structure. It is a temporary, high-entropy coincidence. This paradox forces us to question the low-entropy start of our universe. Why did the cosmos begin in such an orderly state, allowing for billions of years of stability, when a chaotic universe of flickering brains is so much more likely? Cosmologists struggle to resolve this, as it suggests that either our understanding of time and entropy is fundamentally flawed, or we are living in a highly unnatural pocket of existence. We are forced to choose between a universe that is impossibly rare or a reality that is completely fraudulent. Neither option provides the stability we assume when we wake up each morning. Ultimately, the problem of Boltzmann brains leaves us in a state of terminal isolation. It suggests that the most likely state for any conscious entity is to be alone in a void, dreaming of a world that never existed. Every person you have ever known and every event you have ever experienced could be nothing more than the electrical noise of a brain that is currently forming and dissolving in the cold dark of a distant, dying future. You cannot prove you are not a fluctuation. You can only wait for the entropy to reclaim the space your thoughts are currently occupying. The illusion of continuity. You perceive your life as a smooth, unbroken stream of time. Yet physics suggests that time may be a series of discrete frames, and your sense of now is a biological filter for a static block universe. To your senses, the world flows like a river. You experience the transition from one moment to the next as a seamless movement, a continuous happening that carries you from the past into the future. But just as a film reel creates the illusion of motion through the rapid succession of individual static images, the underlying physics of our universe suggests that time is not a flow at all. It is a collection of quanta, discrete, irreducible units of duration known as Planck time. At this scale, approximately 10 to the power of minus 44 seconds, the continuity of your existence dissolves into a series of disconnected snapshots. The mechanism behind this illusion is rooted in how your brain processes information. Human consciousness operates at a significantly slower pace than the fundamental clock of the universe. Your neurons fire in milliseconds, meaning that by the time you perceive a single moment, trillions upon trillions of Planck intervals have already passed. Your biology acts as a smoothing algorithm, stitching these jagged, discrete frames into a coherent narrative of motion and change. You do not feel the gaps between moments for the same reason you do not see the flickering of a high-frequency light bulb. The hardware of your perception is simply not fast enough to detect the strobe light nature of reality. This brings us to the block universe model, a direct consequence of Einstein's relativity. In this view, time is a spatial dimension, similar to height, width, and depth. If you could stand outside the four-dimensional manifold of spacetime, you would see the past, present, and future as a single, unchanging structure. Your birth, your current reading of these words, and your eventual death are all simultaneously there, fixed in specific coordinates within the block. There is no now that moves through the block. Instead, now is merely a coordinate, a marker of where your consciousness is currently localized within a static geometry. The flow of time is not a physical property of the universe. It is a psychological perspective. The implications of a static universe are quietly devastating for our concept of free will and causality.
If the future already exists as a geometric coordinate, then the choices you feel you are making are merely the act of traversing a pre-written path. You are like a needle on a record, believing the music is being created in the moment of contact, when in reality, the entire symphony is already etched into the vinyl. The sense of anticipation, the fear of the unknown, and the regret of the past are all artifacts of your inability to see the block as a whole. You are trapped in a sequential experience of a non-sequential reality. Furthermore, the discrete nature of time suggests that your identity is not a continuous self, but a sequence of related versions of you. The you of a nanosecond ago is a distinct frame in the block, separate from the you of the present. These frames are held together by memory and the physical laws that dictate how one frame influences the next, but there is no essence that travels between them. You are a series of static states, flickering in and out of existence so rapidly that you mistake the sequence for a soul. The stream of consciousness is a trick of the light. We are left with a reality that is fundamentally frozen. The motion you see and the time you feel are the result of a biological limitation, a necessary filter that prevents your mind from being overwhelmed by the totality of the four-dimensional manifold. You live in the intervals between the frames, convinced of a continuity that the physics of the Planck scale and the geometry of relativity flatly deny. The world is not happening. It simply is. The block universe and eternalism. If time is a dimension similar to space, then every moment of your past and future is equally real and currently existing, trapped in a geometric structure that never changes. This concept, derived from the special theory of relativity, is known as eternalism. In our intuitive understanding of life, we view the past as a ghostly record that has ceased to exist, and the future as a void of potential that has yet to happen. We privilege the now as the only slice of reality that possesses the quality of existence. However, Einstein's equations suggest that the division between past, present, and future is merely a persistent illusion. If you were to move at a significant fraction of the speed of light, or stand near a massive gravitational source, your now would slice through the universe at a different angle than someone else's. For your now to be their future, and their now to be your past, all those moments must be simultaneously and eternally present. The mechanism that forces this conclusion is the relativity of simultaneity. Because there is no universal clock ticking at the center of the cosmos, two observers moving relative to each other will never agree on which events happen at the same time. If existence were limited only to a moving now, then which now would be the real one? The mathematics offers no preference. To avoid a logical contradiction, where an event both exists and does not exist, physics adopts the model of the block universe. In this four-dimensional manifold, time does not pass. Instead, the universe is a static, frozen block of spacetime. Your birth is not over, and your death is not coming. They are simply coordinates, fixed forever at specific locations in the geometry of the block. This realization renders the concept of change entirely subjective. When you watch a candle burn down, you perceive a transformation of state. But in the block universe, the candle is a four-dimensional object, a world tube that exists in its entirety. One end of the tube is a tall, unlit wick. The other end is a puddle of wax. The burning is merely the way your consciousness traverses the length of that object.
You are a three-dimensional slice moving through a four-dimensional solid. The candle is not changing. You are simply experiencing its different parts in a specific order. Every moment of your life, from your first breath to your last, is a permanent feature of the cosmos, as enduring as a mountain range. The implications for human agency and the nature of tragedy are quietly unsettling. If the future is already there, then the events of tomorrow are as immutable as the events of yesterday. We treat the future as something we can shape through effort and will, but in a static block, the shape of the future is already defined. Every triumph and every catastrophe is already etched into the fabric of reality. We are like characters in a book who believe they are making decisions, unaware that the final chapter is already printed and bound. The sensation of making a choice is simply the experience of the information becoming available to your localized consciousness as it moves along its world line. Furthermore, Eternalism challenges the very nature of loss. If no moment ever truly vanishes, then the people we have lost and the versions of ourselves that have passed are not gone in any fundamental sense. They are simply located at coordinates that we no longer inhabit. However, this offers no comfort, as it also implies that every moment of suffering is also eternal. A moment of pain does not disappear into the past. It remains forever a part of the static structure of the universe. The block does not heal. It merely accumulates. We are left with a universe that is a finished masterpiece or a completed prison. The flow of time that defines the human experience is a psychological artifact, a biological necessity that allows us to process a four-dimensional reality in three-dimensional increments. We are trapped in a sequence of nows, blinded to the totality of a universe that is already complete. The terrifying truth of the block universe is that while we feel we are moving through time, we are actually standing still in a reality that was finished before we were born. Decoherence and the appearance of solidity. The reason you do not fall through the floor is not because the floor is solid in a fundamental sense, but because the environment has interacted with the atoms, forcing a localized state. In the quantum realm, particles do not possess definite locations. They exist as probability waves, smeared across space in a state of superposition. If the floor were left in a state of perfect isolation, its atoms would behave like ripples in a pond, existing in multiple places at once. However, we live in a noisy universe. Every trillionth of a second, the atoms in the floor are bombarded by photons, air molecules, and cosmic rays. This constant bombardment acts as a continuous measurement, a process known as decoherence. It is this relentless interaction with the environment that tricks the quantum world into behaving like the classical world we perceive. Decoherence is the bridge between the bizarre, fluid reality of the subatomic and the rigid, dependable reality of the everyday. We often wonder why we don't see chairs in two places at once, or why people don't exhibit wave-like interference patterns. The answer is that a chair is too large to stay quiet. Because it is composed of 1,027 atoms, it is impossible to shield it from the environment. Information about the chair's position is constantly leaking out into the surroundings. The moment a single photon bounces off an object, the universe knows where that object is, and the wave function collapses. Not because of a conscious observer, but because the information has become entangled with the rest of the world. Solidity, therefore, is an emergent property of information leakage. This implies that solidity is a matter of frequency and scale, rather than a fundamental truth of matter. If you could somehow stop every interaction, every thermal vibration, and every stray photon from touching an object, that object would lose its solidity and dissolve back into a ghost-like haze of possibilities. The floor feels solid under your feet only because the decoherence rate is so high that the flicker between quantum states is too fast for any physical system to bypass. We are walking on a surface that is fundamentally empty and indeterminate, held together by the sheer statistical pressure of a quadrillion environmental lookups every nanosecond. The mechanism of decoherence effectively censors the quantum world from our view. It acts as a filter that allows only certain pointer states, stable, localized configurations, to persist in our macroscopic experience. All the other possibilities, the versions of the floor where the atoms are shifted an inch to the left or the right, are cancelled out by the interference of the environment. We are living in a pruned version of reality. The real world is a vast, messy overlap of waves, but decoherence slices through that mess to present us with a clean, navigable, but ultimately simplified 3D environment. This realization changes our relationship with the material world. We are not living in a world of things, but in a world of stable information. The desk in front of you is a persistent calculation being refreshed at a rate that defies human comprehension. If the universe were a computer, decoherence would be the error correction code that prevents the simulation from crashing into a blur of probability. It maintains the rules of the game, like gravity, collision, and boundaries, by ensuring that everything stays in its place through constant mutual observation. Ultimately, the appearance of solidity is a localized consensus. The floor, the walls, and your own body are participating in a massive, involuntary agreement to remain real. We are suspended in a state of high-resolution definition only because the universe is too noisy to allow us to be anything else. We do not fall through the floor because the environment refuses to look away, pinning the atoms of our world into a rigid, singular geometry. Beneath that gaze, however, the void remains, waiting for a silence that will never come. The non-materiality of the atom. As you zoom into the matter of your own hand, you find that you're composed entirely of empty space and fluctuating fields, with no hard center to be found. Our common sense tells us that the world is made of stuff, solid, tangible bits of matter that occupy space. We imagine atoms as tiny billiard balls, and their nuclei as even tinier, denser pellets. But as our instruments have pierced deeper into the heart of the fabric of reality, that image has dissolved. If you were to inflate an atom to the size of a football stadium, the nucleus would be no larger than a marble in the center, and the electrons would be like ghostly gnats buzzing in the distant stands. The rest, over 99.9999% of it, is a vacuum. You are, quite literally, a walking void. The solidity you feel when you press your hands together is not the result of two solid objects making contact. In fact, the atoms of your left hand never actually touch the atoms of your right. Instead, what you experience as a solid barrier is the fierce repulsion of electromagnetic fields. The electrons of one hand
push against the electrons of the other with such
intensity that they cannot be forced any closer. Your sense of touch is not a report on the presence of matter. It is your brain's interpretation of a mathematical tension between invisible force fields. We are like ghosts trying to push through other ghosts, held apart only by the rigid laws of electromagnetism. As we descend further into the subatomic, the situation becomes even more abstract. The protons and neutrons that make up the marble at the center of the stadium are not solid either. They are composed of quarks, which, according to our best theories, have no physical size at all. They are point particles, mathematical singularities that possess properties like mass and charge, but occupy zero volume. When you look for the thing at the center of the thing, you find only more empty space, structured by the interaction of the strong nuclear force. The mass of your body is not even derived from the particles themselves. Most of it comes from the binding energy, raw intensity of the fields that holds these point particles together. This leads to a profound philosophical inversion. Energy is not something that matter has. Matter is something that energy does. According to Einstein's E equals mc squared, mass is simply a highly concentrated form of energy. If you were to turn off the fields that bind you, your physical form would not leave behind a pile of dust. It would vanish into a burst of radiation. You are a standing wave in the quantum fields that permeate the universe. Your hand is not an object, but a localized vibration of the electron field, the quark field, and the gluon field, all humming in a specific, temporary harmony. The realization of non-materiality shatters our classical intuition of place. Because these fields are quantum in nature, the particles they manifest do not exist in specific spots until they are measured. An electron is not a dot orbiting a center. It is a probability cloud that exists everywhere in its shell simultaneously. We are composed of clouds, built from mathematical potentials that only harden into the appearance of matter when they are forced to interact with the environment. We are not made of parts. We are made of patterns. Ultimately, the non-materiality of the atom reveals that the universe is far more thought-like than machine-like. We are the sensory interpretation of a complex, invisible geometry. When you look at your hand, you are seeing a high-level user interface, a representation of data that masks a reality of infinite, vibrating voids. There is no stuff at the bottom of the world. There is only a profound, structured silence, a web of fields that simulate the world we have come to call real. The CMB and the limits of sight. The cosmic microwave background radiation acts as a wall, marking the limit of our observational reality and hiding whatever processes occurred before light could travel freely. For the first 380,000 years of its existence, the universe was a dense, opaque plasma of protons, electrons, and photons. Light could not travel any significant distance without bumping into a charged particle, making the early cosmos a literal fog. It was only when the universe cooled sufficiently for atoms to form, a moment known as recombination, that space became transparent. The CMB is the first light that escaped that fog, a frozen snapshot of the universe at the exact moment it became visible. It is the oldest image we possess, but it also represents a definitive boundary. Beyond this wall of glowing microwave radiation, the universe is hidden in an eternal electromagnetic darkness. This observational limit suggests that our knowledge of the universe's origins is inherently restricted. We can theorize about the Big Bang, inflation, and the first fractions of a second, but we cannot see them using light. The CMB is the horizon of our visual reality. We are like inhabitants of a valley surrounded by high, impenetrable mountains. We can see everything within the valley in exquisite detail, but the terrain beyond the peaks is a matter of mathematical inference rather than direct evidence. This wall is not merely a technical challenge for our telescopes. It is a fundamental feature of the cosmos. The universe has a built-in privacy screen that prevents us from witnessing its own birth. The mechanism of the CMB reveals a universe that was once incredibly uniform. When we look at the temperature fluctuations in the background radiation, we find they are consistent to 1 part in 100,000. These tiny ripples are the seeds of everything we see today, the blueprints for galaxies, stars, and planets. However, the sheer uniformity of the CMB poses a problem. Parts of the sky that are billions of light-years apart have nearly identical temperatures, even though they should never have had time to communicate or exchange heat. This led to the theory of inflation, a period of faster-than-light expansion that smoothed out the universe before the CMB was even emitted. While the math for inflation is compelling, we can never visually verify the pre-CMB era to confirm it. This creates an epistemological crisis. If our primary tool for understanding the universe, light, cannot reach back to the beginning, can we ever claim to know the truth of our origin? The CMB tells us that the universe had a hot, dense beginning, but it also obscures the specific how and why. We are left interpreting the shadows on the wall. Some physicists suggest that gravitational waves might eventually allow us to peer behind the CMB, as gravity would have traveled freely through the early plasma. Until then, however, our reality is a bubble of light bounded by a 13.8 billion-year-old static. The CMB also serves as a reminder of the universe's finite history. The fact that we see this radiation in the microwave spectrum, rather than as visible light, is due to the expansion of space itself stretching the wavelengths over billions of years. This redshift confirms that we live in a dynamic, changing system. But it also implies that information is being lost. As the universe continues to expand, the CMB will eventually become so faint and stretched that it will be undetectable. Future observers, billions of years from now, may look at a dark, empty sky, unaware that a first light ever existed. Our current observational window is a lucky, temporary privilege. Ultimately, the CMB marks the boundary of the map. It is the edge of the world we can prove through observation. By acknowledging this limit, we realize that our scientific narratives are built upon a foundation of unseen events. We are the children of a history that erased its own footsteps, leaving only a faint, glowing echo to hint at the titanic forces that forged the reality we inhabit. The limits of sight are not just a barrier. They are a definition of what it means to be an observer inside a finite system. We can see the fire, but we can never see the spark. Dark matter and the invisible framework. Everything you see and touch constitutes only 5% of the mass energy of the universe, meaning you are an anomaly living within a dark, unobservable structure. For centuries, we believed that the stars, planets, and gas clouds were the primary actors on the cosmic stage. We assumed that if we could see it, we could account for it. However, in the 1970s, as astronomers measured the rotation speeds of galaxies, they encountered a mathematical impossibility. The visible matter in the outskirts of galaxies was moving much too fast. By all laws of gravity, these stars should have been flung into the intergalactic void. There wasn't enough stuff to hold them together. This led to the realization that galaxies are not just clusters of stars, but are embedded within massive, invisible halos of a substance we now call dark matter. The mechanism of dark matter is defined by what it doesn't do. It does not emit, absorb, or reflect light. It doesn't interact with the electromagnetic force at all, which is why it remains invisible to our eyes and our most sensitive telescopes. It is a ghost substance that only reveals itself through the pull of gravity. As we mapped the large-scale structure of the cosmos, we discovered that dark matter is not just a peripheral mystery. It is the fundamental scaffolding of the universe. It formed a cosmic web of filaments in the early universe, and it was the gravitational pull of these invisible threads that drew ordinary gas together to form the first stars and galaxies. Without this dark framework, the visible universe would never have clumped together. The implications for our sense of importance are humbling. We are used to thinking of matter as the stuff of reality, but the data suggests that we, the atoms of the periodic table, are a mere dusting of baryonic soot on a much grander, hidden architecture. If the universe were a vast ocean, everything we have ever observed is just the foam on the tips of the waves. The deep, heavy currents that actually drive the system are entirely beyond our sensory reach. This creates a profound cosmic provincialism. We are attempting to understand the laws of the universe by studying the 5% minority. It is like trying to understand the ecology of Earth by looking only at the birds in the sky, completely unaware of the forests and oceans below. This leads to the question of what dark matter actually is. We suspect it is composed of particles that fall outside the standard model of physics, such as WIMPs, weakly interacting massive particles, or axions. These particles are passing through you right now by the billions every single second. Because they do not interact with your atoms via the electromagnetic force, they pass through your body as if you were empty space. We are living in a dual-layer reality, a bright, energetic layer of light and atoms, but we perceive, and a dark, silent layer that provides the gravitational glue for everything we know. The two worlds occupy the same space, but remain functionally blind to one another. The presence of dark matter also forces us to rethink the ultimate fate of the universe. Because it provides the bulk of the pull in the cosmos, its density determines how quickly the universe expands, or if it will eventually collapse. However, even dark matter is overshadowed by the even more mysterious dark energy, which makes up the remaining 68% of the universe and acts as a repulsive force. Between the invisible scaffolding of dark matter and the stretching force of dark energy, normal matter is a tiny, fragile passenger. We are an accidental byproduct of a dark, indifferent machine. Ultimately, the invisible framework reminds us that our reality is a curated experience. Evolution has tuned our senses to perceive the 5% of the universe that we can eat, breathe, or bump into. The remaining 95% is a mathematical necessity that we can calculate, but never truly see. We are the outliers, the rare exceptions to the rule of darkness. To look at the night sky and see the stars is to see the ornaments on a dark tree. The tree itself is what holds the ornaments up, yet it remains forever hidden in the shadows of the unknown. The silent universe. Despite the vastness of the observable sphere, we find a universe that is mathematically perfect, yet biologically silent, leaving us to wonder if the reality we see is simply a localized fluke in a dead system. For over half a century, our most sensitive radio telescopes have been pointed toward the heavens, scanning for the slightest whisper of a non-natural signal. We have mapped billions of stars and confirmed thousands of exoplanets, many of them sitting comfortably in the Goldilocks zone where liquid water can exist. Yet, the cosmic silence, known as the Fermi paradox, remains absolute. The math tells us the universe should be teeming with life, but the data shows us a graveyard of sterile gas and radiation. We are faced with the chilling possibility that the great silence is not a temporary technical hurdle, but a fundamental property of the cosmos. The mechanism behind this silence is often attributed to a great filter, a developmental barrier so difficult to overcome that it prevents life from ever becoming a spacefaring civilization. This filter could be in our past, meaning the emergence of complex life is an almost impossible miracle, or it could be in our future, suggesting that all civilizations inevitably destroy themselves before they can make their mark on the galaxy. If the filter is ahead of us, then our current reality is merely a brief, flickering moment of awareness before the inevitable return to entropy. The perfection of the laws of physics, which allow for the formation of heavy elements and stable orbits, seems to serve no purpose other than to host a vast, empty museum of matter. This leads to the realization that the universe is not designed for us or for life at all. When we look at the scales involved, the biologically active portion of the universe is an infinitesimal fraction of the whole. Life is a thin, fragile film on the surface of a few rare rocks, while the remaining 99.9999% of the cosmos is a lethal environment of high-energy radiation, vacuum, and extreme temperatures. We are the anomaly, not the rule. If the universe is a mathematical output, as previous sections suggest, then life might be nothing more than a rounding error, a chaotic byproduct of equations that were never intended to produce a conscious observer. The psychological impact of the silent universe is a form of cosmic loneliness. In a relational universe, as we've discussed, properties exist because of interactions. If there is no one else to measure the cosmos, and if we are the only observers, then the entire reality of the galaxy depends on a single, isolated species. This places a terrifying burden on our existence. If humanity were to vanish, the meaning of the Milky Way would vanish with it, leaving behind a series of physical interactions that no one is there to interpret. We are the only part of the universe that has woken up, but we have woken up in a house that appears to be completely empty. Furthermore, the silence suggests that intelligence might not be a favorable outcome in the long-term calculation of the universe. While we view our consciousness as the pinnacle of evolution, the lack of other civilizations suggests that high-level intelligence may be a self-terminating trait. The very mathematical laws that allowed us to build radio telescopes also allowed us to build weapons of mass destruction and unravel our own climate. The mathematical perfection of the universe includes the laws of thermodynamics, which dictate that all systems tend toward disorder. Our biological fluke may be a temporary protest against an overwhelming entropic silence. Ultimately, The silent universe forces us to reconsider the value of our localized reality. We are the only ones currently rendering the universe into a coherent story. The silence is not a void to be feared, but a boundary that defines our significance. We are the small, bright exception to a dark and silent rule. If the universe is a calculated output, we are the only part of that calculation that is aware it is being solved. The silence isn't an absence of life. It is a testament to the staggering, improbable miracle that we are here to hear it at all.